For the instructions to be performed, which are indeed stored in the instruction memory, we have some specifications to be provided. The specifications that we have for the instruction will include the name of the instruction, the OP code for the instruction, which will be indeed stored in the instruction set architecture format that we just discussed. And then we will have a shorthand name for the OP code, which is called as mnemonic, which will be indeed a symbolic way of referring to that instruction. And then we will have a specification for the instruction format. Okay, what's the format of the instruction? We will see the examples later. We also, the specification indeed provides a register transfer description of the instruction, and finally a listing of the status bits that are meaningful, okay, during an instruction's execution. So over here you can see examples of instruction specification. Here we have, for example, the instruction which is move A. The OP code for it is all zeros. So we have 0 as the OP code. The mnemonic, the symbolic instruction is move A, and the format is given here. The format is RDRA, and the description is transferring the content of the register with the address of source A to the register with the address of destination DR or destination register. And the status bits that are involved are N and Z, the negative and 0. The next one that to consider is the increment. When we have the increment instruction, the OP code for it is 1. The symbolic mnemonic is INC or INC. The format is RD and RA, and the description is provided here. So whatever value we have in the register with the address of source A is incremented, 1 is added into it, and then the result is stored in the register with the address of DR or destination register. So I'll go through some of them as well. Then we have the add instruction. The OP code for it is 2. Mnemonic is ADD or add. The format is RD, RA, RB. It includes 3 registers. So the content of the register with the address as SA is added to the register with the address as SB, and then the result is stored in the register with the address of DR. So these are the transferring and arithmetic operations, examples of them. And then here we have the logical operations, and for which the OP code is given here, which is 8. The mnemonic is AND. We have RD, RA, RB, 3 registers are involved. The bitwise AND of the content of 2 registers is performed, and the result is stored in the register with the address DR. You can also see the next indeed logical operations. For all these logical operations, indeed for the ones that you see a star over here, the content of the program counter is incremented by 1, so the next instruction will be executed afterwards. And over here you can see some shift operations. For example, we have the shift right or SHR operation with the OP code given here, which is 13. OP code is 13. The format uses RD and RB, so 2 registers are involved. Keep in mind that we have source B here. So the content of the register specified by source B is shifted towards the right by 1 bit position, and the result is stored in the register with the address determined by DR. Then we have load immediate and add immediate, which use some constant value as the second input to them. You can see the OP code here. The mnemonic is also provided, LDI, ADI. the format is specified here. When we have the load immediate, if you remember, we had access to some constant value coming from the instruction. We will have the 0 field, and then because for OP we have only 3 bits, 3 bits only here, then it will be filled by zeros, and then the register with the address of DR, destination register, will indeed contain the resulting value. Then we have the load and store instructions as well. The description is provided here. When we have the load instruction, they are different. When we have the load instruction, you can see that the register with the address of destination register is loaded by the memory location with the given address which is in the source A. While for the store, indeed we have the opposite way. In the case of load, we load the register by some value coming from the memory, and in the case of store, we store some value that we have in the register into the memory. And in the next operations, we have the branch on 0, branch on negative, and jump instructions. You can see the OP code for all three over here, and then the mnemonics are also given: BRZ, BRN, and JMP. The format is given, so you can see that for branch on 0 or BRZ, we have this case. If what we have in source A is equal to 0, in the register with the address of source A is equal to 0, then the program counter will be updated. How it is updated? It will receive indeed what we have in the so we should indeed go back and have a look at what we had for the jump and branch format. OP code is CM. This is what we have for jump and branch, and we were using what we had here for the address. By combining them, this would give us the offset that we have for the branching or for the program counter. So it will be added into the original value that we had for PC, and then the new PC will be determined. But this is a conditional branch, so it is branch on 0. The content of the source A that we have here will be checked if it's equal to 0. So keep in mind that again this will be an address. So over here we will have an address SA. The content of the register with that address will be checked. If it's equal to 0, then we will have this branching. In the case of branch on negative, with this OP code, we will check to see whether that value is negative. If it's negative, then the branching will be done. If it's not negative, then the content of the program counter will be incremented, which we had also for the previous case. In the case of jump, we don't have condition on jumping. When we have this OP code received, the jump will be performed, and then the content of the program counter will be updated. Over here we have an example in which a set of instructions are provided. You can see the decimal address in the memory for each instruction. So a couple of them are shown here indeed. And the decimal address of 25, the content of the memory is provided here. And you can see that over here indeed we have the OP code. So the first 7 bits determine the OP code for the instructions. Then we have, depending on the ISA format indeed, we have the next 3 fields. This also would depend on the operation. OP code that we have for the first case here at the position 25 is 5. So 0, 0, 0, this is 5 indeed. And 5 OP code means that we are going to have the subtraction. For subtraction, we need 3 fields as destination register, source A, and source B. Destination register is 1. That's what we have here. Source A is 2. So here we have 2. And source B is 3. And then the operation is performed in this way. R2 minus R3, source A minus source B, and then the result is stored in the destination register. In the second example, in line 35 that you see here, in the memory position in the 35, we have the OP code as 32. This 32 means storing. Okay? And then the format that we have for storing is like this. The memory location with the address which comes from SA will receive the value which comes from SP. SA and SP are determined here. This is SA and here we have SP. So SA comes from here and SP, which is 5, comes from here. So for this OP code, we don't have the destination register used, so this is not important. It's filled by zeros. And you can see how the loading is performed. The next one to consider is the OP code of 66, which is add immediate. In the case of add immediate, we have the destination register determined here, which is 2. So R2 is determined. It will receive, we have 7 here, which is source A, and source A is 7. It means that we will have R7 plus some immediate value, which is determined as 3. So R7 plus R3. So you can see that how you can refer to the memory content for an instruction and then determine what operation will be performed. The next one to consider is the OP code of 11000000, which is 96 decimal, and it is for branch on 0. Branch on 0 means that the content of the register with this address, which is 6, so if R6, which is determined here, is equal to 0, then program counter will be updated by the current program counter plus this value that we have here. And the value that we have here is determined here. Indeed, it is 11001100. Keep in mind that this is signed 2's complement, so this is some negative value. Okay, if you want to find out the positive value, indeed the actual value, it corresponds to minus 20, which is shown here. So if R6 is equal to 0, then the program counter will be updated by PC minus 20. So we were here at 55. We will go back to 35 if R6 is equal to 0. Okay, so that is a conditional branching indeed. We can also have a look at the data memory at this address 70. For the data, we have 192, and after execution of the instruction in line 35, which we have here, it will be equal to 80. Why? Because in line 35, in the memory address 35, we have a memory address with the address, memory location with the address of R4 will receive the content that we have in R5. In R5, we already had 80, and R4 is equal to 70. So at this address 70, the content will be updated by what we have here as 80. So after the execution of this, the content of this memory address will be equal to 80. So these were indeed some examples of how an instruction could be seen in the form of a set of bits.